Okay, dear student. So, today we will discuss about a very well known deadlock avoidance strategies. And the very well known algorithm is called Banker's algorithm. The name was chosen because the algorithm could be used in a banking system to ensure that the bank never allocate its available cash in such a way that it could not no longer satisfy the need of all its customers. So banker's algorithm is mainly used for deadlock avoidance purpose. This question comes in different types of competitive exam also. So the question is like that: banker's algorithm is used for deadlock avoidance or deadlock prevention purpose. The simple idea or the simple concept to remember this thing is just like our alphabet format A B C D. A for avoidance, B for bankers. Okay, this is the simple tricks. Now, we'll just focus this algorithm. The data structure consists of four types of variable: available, the system availability, the maximum resource, max, the allocation, the resource which is already allocated, and the need of particular process. And here you note down one thing: we will calculate the need based on max minus allocation. In this algorithm, we use two types of variable, AN and AIM. AN is the number of processes and AIM is the number of process type. Okay, now we focus on the algorithm. First, Banker's algorithm is two types. First one is safety algorithm and second one is resource allocation algorithm. So, first we discuss about safety algorithm. In safety algorithm, here we use two vector, work and finish. The system availability is stored in work variable, and initially the finish will be in false state. Here I stands for the prefix of process, like process P0, P1, P2 dot Pn minus 1. Then in next step, our first objective will check when say process P0 is requesting for any resources from the system, we will check the need of that process I is less than equals to work. If the condition is true, then we can say that the system is in safe state. As the definition suggests of safety concept, the requesting resource the requesting resource is always less than equals to available or work. So then the finish of this process I is false. Then the third step will be work is equal to work plus allocation. Work is actually the available. So the current or actual present availability is equals to previous availability plus allocation of that process I. Then you will check the finish is true or not. If the all process are satisfied this condition, then we can say the system is in safe state. So this is the basic algorithmic structure. The algorithm is an abstract version of the entire picture. It doesn't clear to everyone. If we actually deal with the proper example, then it will much more clear for us. So now we'll give an example. In this case study 2, look at that problem. Here 5 processes are there: process P0 to P4, their allocation, max, need, and available matrix are mentioned. Here look at that. For example, availability. It has different instances. Like in the initial definition, process is an instance of a program in execution. Like so, each and individual process may have several instances. So in that case, the system availability have in that problem it has three different types of instances, A, B and C. So in that problem, first question is find out the need matrix. And as I told you earlier that need equals to max minus allocation. So we will try to calculate the need matrix. So here we will form the need matrix. You will check it very minutely that for process P0 the max is the instance of A of max is 7 and the allocation is A of A is 0, 7 minus 0, so the need of instance A is 7. Similarly 1 minus 3 minus 1, that is similarly for 5 minus 1, that is 4, and 3 minus 0, that is 3. Now here the next two other questions will frequently arise. Whether your system is in safe state. If your system is in safe state, then what is the safe sequence of order? So now we'll check. First we check for process P0. Based on the Banker's algorithm, Banker safety algorithm, we'll first check the need. What is the need of process P0? Need of process P0 is 743, which is less than equal to system availability. System available having 332. So the answer is false. So process P0 is in waiting queue or waiting state, and we increment the value of Pi by I plus 1. So the next we check P1. So P0 is in waiting state. Next we check P1. The need of P1 is what? 1, 2, 2, which is less than equal to present system availability 332. The answer is true, yes. So the current availability will be updated based on the previous availability, that is 332, and the allocation of P1, that is 200. These two matrices are added and the new availability will be 532. So P1 successfully completed its entire task. So it will move to safe sequence of order, the first element of safe sequence of order, and P1 task will be completed. So we cross it, the process of P1. Now next we move to process P2. The request or the need of P2 is 600, which is less than available system availability 532. The answer is false. So P2 is in waiting state. So again we move to the next state, that is P3. So the need of P3 is 011, which is less than equals to system availability, that is 532. The answer is true. So we update the system availability by previous availability plus the allocation of P3. So the new availability will be 743 and P3 moves to the second element of safe sequence of order. And next we move on P4. The need of P4 is 431 and the present system availability is 743. So this condition is also true. So we can assign that particular process, that particular resource to the particular process, and we update the current availability. So the current availability will be previous availability, that is 743 plus the allocation of P4 002. The modified present availability will be 745, and P4 will move to the third element of safe sequence of order. So again we move to the queue, focus on the queue. P0 is already waiting. So we'll check the need of P0, that is 743, is less than or equal to present availability, that is 745. Then the answer is true. So we can allocate it and the current and update the present availability by adding with previous availability with allocation of process P0, and the new availability will be 755, right? Now, so P0 is in the fourth element of the safe sequence of order, and we move on the last part, that is P2. The requirement or the need of P2 is 600 and the availability will be 755. The condition is true, that is less than equals to the present availability. So we update the present system availability by adding or sum of the previous availability plus allocation. So the new availability will be 1057 and P2 is in the fourth element of the safe sequence of order. So this is in that particular step by step we can achieve the whether and check whether the system is a safe state or not, and what is the safe sequence of order. So now we can say that the system is in safe state and the safe sequence of order is P1, P3, P4, P0, P2. So dear students, I think this example is quite good enough to understand how we handle this Banker's algorithm with respect to safe sequence of order. Thank you all.